So in biological systems, we have a lot of alcohols. And so alcohol, you know, that's a pretty strong base there. It's not very stable, not horribly unstable, but it's not very stable. And so this reaction actually wouldn't proceed forward. It would favor the back reaction, right? The hydroxide coming in and attacking, because the chloride negative is more stable. So if I wanted to do this reaction, what I need to do is make the alcohol a better leaving group. And I can do that in a few fashions. One is to react it and turn it into an acid, react it with an acid. So if I react it with HCl, first step I'm doing is I'm actually having the alcohol react with the acid. So this is an acid-base reaction where the alcohol is picking up a proton. Leaving group's leaving, the chloride's leaving. That gives me now the protonated form, right? The hydronium here. Now, in this case, this is secondary. Under the conditions I'm reacting this in, this is actually likely going to be an SN1. Why? I have, let me pull a different color, right? I have a secondary substrate. This is aqueous, right? So my solvent. I have secondary. I've got a good nucleophile. I've got a good leaving group. But because it's secondary in a protic solvent, I might be able to get this to go SN2, but it's going to favor an SN1 reaction, which means the first step is actually leaving group leaving. And then the chloride comes in. Attacks the carbocation. Give me my product. So that's one activation, is doing the acid. Now, if we had started with a stereospecific substrate, if I had reacted this with HCl, then I'm going to end up with likely a mixture of the reactant. I might be able to get this to go a little bit SN2 so that inversion is a little higher than retention, but there's almost no way to guarantee that this is only going to go through SN2. So therefore, I'm going to get both products. So the first step is acidic. Notice that here the chloride is nucleophilic. This is going to be different when we get to eliminations, right? We're going to still do an activation process, but that activation process for eliminations will have a non-nucleophilic anion. For acid reactions, right, the only choice we really have is that once we form that acid, it has to react right away, right? So when we're looking at this, whatever is attached to that acidic position is the thing that's going to add. The other thing we need to know is that that acid has to be strong enough to fully protonate the water. So a weaker acid, even something like carboxylic acid, probably isn't going to do it. So we're really limited here in the number of acids that could work. Hydrochloric could work, hydrobromic could work, hydroiodic would work. But if we look at something like sulfuric acid or phosphoric acid, sulfuric acid is a non-nucleophilic group. So the sulfonate group would not attack the electrophile. Same thing with phosphate. We'll see those when we get to eliminations. Okay. So we have a limited group. So we need another way to activate these, and that's when we get to the sulfonates. We talked a little bit about the sulfonate esters. Let's look at the reaction. And this is shorthand. I'll show it in a second what tosyl chloride means, the TSCl. In this case, we've set up the second step to be an SN2 style step. And we've also opened this up to lots of different nucleophiles, right? So now it doesn't have to be the anion of the acid. I can use any nucleophile I want in the second step. So first step is activation. Second step is second, not even step, second total reaction is going to be adding my nucleophilic group. Okay, so the TSCl is this sulfonic ester with a toluene on it. So we call it a tosylate or a tosyl chloride. And then at this position, so what we've done is we've acted at the sulfur. So lone pair reacts at the sulfur. Lone pair goes up. Then in the next step, the electrons come down from the oxygen. They kick off the best leaving group, and the best leaving group turns out to be the chloride. Let me keep my stereochemistry here. Right. And then the pyridine, that's what the PY is. Pyridine is shorthand for pyridine. PY is shorthand for pyridine. Remember, we talked about that one as a proton sink. That's what it's doing here. It's just picking up that proton so that I can form the stable molecule, the sulfonate ester. So the alcohol reacts with the sulfur. Pi bond leaves. Second step, pi bond comes back down, kicks off the chloride. Pyridine picks up the proton to get us to the stable sulfonate ester. And the shorthand for this, right, is the OTS, right? So all of this structure here, right, is the TS. So the tosyl group. Once we have that formed, right, then in another reaction, so this is the activation step. This next step is then going to be the substitution. So we take that activated alcohol group, which is now the sulfonate ester, and then we get an SN2 type reaction. This is a good SN2 style leaving group. It's a big and polar. Yes, ma'am. No, the sulfonate ester is more stable because I can delocalize that oxygen negative to the other oxygens. So not only so I have 3 different resonance structures for that. I also, on the tosylate, can resonate that potentially into the ring. So the advantage of this one is it is 2 different reactions, right? We're making the sulfonate ester. We can put the sulfonate ester in a bottle. It's pretty stable. And then we can add the nucleophile in the, so it does take 2 steps. But the nice thing about this one is that it's going, I can set everything up for it to be an SN2 style reaction, right? And therefore I'm going to get only inversion here. And the other one, I have a limited number of potential reactions because I have limited number of strong acids with nucleophilic groups attached. Now, what you could do in the top one, right, is once we've done this, right, now we have a chloride. The chloride's a good leaving group. So now we could take the chloride and react it with something else to do the substitution. So I could add HBr, iodine, or HCl, and then in the second reaction, add a different nucleophile to displace the halide that I've added. Okay. All right, so sulfonate esters. So you have the tosylate. So the tosyl chloride is this one. And again, that's the abbreviation we use. Can also have a mesylate. And you'll also see that one quite a bit, right? So if you see the TS or the MS, right, that's what, they're both sulfonate esters. Oh, thanks. Get rid of that. Okay, questions? Okay, other questions? All right. The other thing we need to spend a little time on is carbocation rearrangements. And this one's really ugly, so I'll redraw that one. So if I did this SN1 reaction, there's a possibility that my substrate gets modified, right? So what I think should be the product, which is this, right? Just the direct substitution of the chloride with the alcohol, I end up with another product. And in many cases, this other product turns out to be the major product. So what's happening here is the fact that I'm going through an SN1, I'm going through a carbocation. Remember, carbocations are high energy species, and high energy species want to be stabilized. So first step is that the leaving group's leaving, right? We add heat or whatever we need to activate that to proceed. We end up with this carbocation. Now, if we think about carbocation stability, we know that a secondary carbocation that's not what I want to draw. We know that a carbocation, right, can be stabilized by the hyperconjugation to that sp3 carbon. That's why a tertiary carbocation is more stable than a secondary carbocation is more stable than a primary carbocation, right? Because I have that sp3 carbon electron density that can back donate, right, to the pi system, the pi bond, the pi of the carbocation. What I have in this case is I have a secondary carbocation next to a quaternary carbon, right? So this carbon right here has 4 different carbons attached. Well, if we think about this group here, it means that there's going to be an overlap with that CH3, right? So that's going to be overlapping. Because of that overlap, what can happen here is that I can get a rearrangement right? So it's an internal reaction of that substrate that I get a rearrangement so that I get to a more stable product. And here we can see that we've now gone to a tertiary. So I've moved one of those methyl groups over to the carbocation to give me a tertiary carbocation. And which of the 2 carbocations is going to be more stable, the secondary carbocation or the tertiary carbocation? Tertiary. So whenever I form a carbocation, I always have the possibility of a rearrangement. Sometimes those will happen and sometimes they won't. They'll happen when the rearrangement stabilizes the carbocation. They tend not to happen if the rearrangement wouldn't do anything to stabilize the carbocation. So if I had a secondary and a tertiary next to each other, could there be a rearrangement? Yes. But the result of a rearrangement would still be a secondary carbocation. So I'd be going from secondary carbocation to secondary carbocation, right? So let's show that, getting a few blank stares. So if I had this carbocation and I was going to rearrange it to this carbocation, and let's put something out there, right? I'm really going from a secondary carbocation to a secondary carbocation. Could that rearrange? Yes. Is there a driving force for this to rearrange? No. if I had the possibility of going from a secondary, right, to a quaternary, and that's the most obvious one, then what's happening is I'm going from a secondary, right, to a tertiary. So there's going to be stabilization there, and that's going to be something that's probably going to happen. Now, it doesn't happen very often because it's primary, but you could also think about it as a primary, potentially a stabilized primary, with a tertiary going to a secondary. Again, less likely, but there are some conditions where that could occur. So when you look at these, if you're looking at it, it's pretty straightforward. If there's a difference of 2, then a carbocation rearrangement is going to give you a more stable species. So if I have a secondary next to a quaternary, then the result would be a tertiary that's stabilized, right? If I have a primary next to a tertiary, again, primary is difficult, but that would end up in a rearrangement. And sometimes the rearrangement is the reason that a primary might work, right? And so usually what we're going to be looking at is the secondary next to a quaternary, and which is the example I showed you, right? So a difference of 2, we then go to a 3. A difference of 2, right? Then we go to a 2, right? So once we have this carbocation, right, then the carbocation then does the reaction. So in this case, I have my original carbocation and I have my rearranged carbocation. And then those react with the nucleophile. So first step, nucleophile attacks electrophile. And then to complete this, we get a proton transfer. Again, this is a solvolysis. My solvent is my nucleophile. So last step, proton transfer. And then this is the major product. From the more stable carbocation. So one of the sets of questions you'll see on online homework will be, what is the major product? What they're trying to get there in an SN1 type reaction is, can you determine what the more stable carbocation is? So the more stable carbocation intermediate is going to be what's going to end up giving you the major product. So between these two, we have a secondary and a tertiary. So that one is more stable. Okay, questions about that? So if you had inductive effects, yeah, you'd have to also take that into account, right? So if I had an electron withdrawing group, that would destabilize the carbocation. The other rearrangements you'll see are in acyclics. I'm not saying I can't think of the word. Is going to be whenever you have stabilized carbocations. Taking up too much space. So if we look at this reaction, right, we have an alcohol. It's going to be allylic. That's the word I'm looking for. Allylic. Okay, allylic means that it's one away from a double bond. So if we look at the reaction here, the lone pair can come in, attack the hydrogen, chlorine leaves. That makes the hydronium. Since this is an allylic position, I could get the carbocation to leave. Again, primary, so we still have a possibility for SN2. Get this carbocation, but this carbocation is in resonance with this carbocation. So this isn't really a rearrangement as far as carbon skeleton, but it does give you a different product, right? Because I have two resonance structures. So this resonance structure, again, if we're looking at these two, this is a primary allylic, right? The fact that it's allylic is a reason that this is plausible. Here we have a secondary, and which of those two is going to be more stable? The secondary position is going to be more stable. And then to finish off the reaction, the chloride comes in and attacks the carbocation, right, to give me my two substrates. If we look here, this one's going to be the major product, and this would be the minor product. Again, due to the stability of the carbocation. So when you're dealing with SN1 reactions, there's times when you're going to get substitutions that are not exactly what you would have thought, right? They're not direct substitutions. With SN2s, I'm not going through a carbocation. I don't expect to get a rearrangement. There are some rare cases of rearrangements, but you're not going to see them until you get to grad school. For SN1, rearrangements occur all the time because I have a carbocation, it's a high energy species, right? We have a high energy reaction, and then that's going to end up giving me a different product. And then what the type of question you'll often see is which one of those two products is major, right? They'll ask you how to explain it. You explain it by a rearrangement or a resonance structure from a carbocation. Then it'll ask you which one is the more stable. The way you answer that is, which one is the major product? You answer that by looking at the stability of carbocation. And the stability of carbocation, again, is related to whether it is allylic, right, next to a double bond, or is it primary, secondary, tertiary? Questions about rearrangements? Okay. There's some practice online and in the book. So just got to remember to break it down and think about what's happening in the product. If you just stare at the reactant products, the products of the reaction, you're not going to be able to figure it out, obviously. What you have to do is go back through the mechanism and look at the mechanism. The mechanism is going to help you figure it out. So one of the things that we've been doing, right, is comparing these two, and you're going to have to be able to identify what is the most likely reaction. Is it most likely going to go through an SN1 or an SN2? In some cases, the products are going to be look the same, right? If it's a substitution, if I'm substituting a chloride for an alcohol, that may look the same. If I'm substituting a chloride for a cyanide, that might be the same. But the mechanism behind those substitutions, right, can determine the stereochemistry, can determine whether I get rearrangements, regiochemistry, right? It can determine several things about the product. So one of the things you have to do is predict whether a reaction will most likely proceed through an SN1 or will most likely proceed through an SN2. For SN2, there's some straightforward ones. One, unhindered substrates. So that's your electrophile. So your methyls and your primaries. So the rate of the SN2 reaction really has both the nucleophile and the substrate in it. And if I can hinder the backside attack, the anti-orbital attack of the nucleophile, that's really going to slow the SN2 reaction down. So SN2, what will favor SN2 is unhindered electrophiles. Your book says powerful. I'd say good nucleophilic, but powerful anionic. For the reaction to actually proceed in an SN2, the first step is the nucleophile attacking the electrophile and the leaving group leaving, right? So if the nucleophile does not want to have a reaction to occur, then it's going to be slower, right? So therefore, that could favor an SN1 over an SN2. So good, powerful anionic nucleophiles. And then polar aprotic solvents. SN2 is a lower energy reaction. The solvation of my components is necessary, but the stabilization of my components is not. I'm not going through a carbocation, so my solvent's not going to play a big part in stabilization of that carbocation. I need everything to be well dissolved. That's why it says polar aprotic solvents. Again, because I'm most often going to have anionic nucleophiles, but I don't need to stabilize my intermediates because my intermediates are partially positive and partially negative. It's in this polarized state, not a full positive and a full negative state. For SN1, need hindered electrophiles. Now, do hindered electrophiles speed up an SN1 reaction? No, they slow down an SN2 reaction, right? So it's no longer illegal, but one of the things they used to do is if you had a big, heavy offensive line and the other team was really had a smaller defensive line or was known as a fast team, what would they do the day or two before the game? They'd water the field or hope it rained, right? So you just make sure you water it a little extra 30 minutes or something, and all of a sudden the football field gets really sloppy. That doesn't make your players better, but it makes their players worse, right? It slows them down, and you don't have to worry about that. So in an SN1, a hindered electrophile does not help an SN1. It slows down an SN2, right? And so one of the things to think about here is not that an SN2 is always possible or an SN1 is possible, but that it really has to do with rates. That for an SN1 to occur, that's a high energy state, which means that if the way I set up the reaction slows down an SN2, then an SN1 is more likely to occur. And so this first one is not And this is one of those things that SN1 likes hindered electrophiles. No, SN1 doesn't like hindered electrophiles, but SN2 can't work with hindered electrophiles. So therefore that drives the reaction to the SN1. Okay, so slightly, it's more on the negative side. Potential for a stable carbocation. Okay, so tertiary, secondary, or resonance stabilized. Right, so stable carbocation, that's that if there's not a possibility to stabilize carbocation, then you're not going to have an SN1 occur. Uncharged nucleophiles. The rate law for an SN1 does not include the nucleophile, so therefore the nucleophile is not in the rate determining step. So therefore weaker nucleophiles, non-charged nucleophiles such as water, can be water, methanol, alcohols can all be very good nucleophiles because they're not in the rate determining step. And in SN2, they're an integral part of the rate determining step, so therefore they need to be better. And then protic solvents. Protic solvent is going to stabilize the carbocation, right? So there is charges that need to be stabilized. This can stabilize that carbocation. So therefore protic solvents, so water, methanol, ethanol, things like that are going to be favored for SN1. So substrate, right? I analyze your substrate, analyze your nucleophile, analyze your leaving group, analyze your solvent. There's other things that could be in there, such as temperature. If we think about SN2, is that a low or a high energy reaction? That's a lower energy reaction. Is it necessary to add heat? No. For an SN1, is it necessary to add heat? Well, that's a high energy reaction. Heat would help that reaction, right? So you also have some things. So whenever you're getting a question of asking whether something's going through SN1 or SN2, or if it's actually asking you to predict stereochemistry, what you need to be thinking about is this an SN1 or SN2? So they can sometimes, they don't directly ask whether it's SN1 or SN2, they say predict the stereochemistry. The thing that you have to say is this an SN1 or SN2? Because they have two different stereochemistries. And then go through that list of things. Start with your substrate, go to your nucleophile, go to your leaving group, look at your solvent if there is one provided, and look at any other conditions if they're provided. Usually temperature is the other condition. No temperature or low temperature, SN2, high temperature, SN1, right? Now, where students get in trouble when they're comparing SN1, SN2 is you will look at one and stop. So remember when we were doing stabilization of acids and bases, and we used the atom, right? The resonance, inductive, and then orbital. Same thing here. You need to go through the whole process. You need to look at your substrate. What does that say? We need to look at our nucleophile. What does that say? What does the leaving group say? What does the solvent say, if there is a solvent? What do the conditions say? Then after you have all that information, you need to put those all together and then come up with a suggestion. The tendency that students have is to pick one. You fixate on solvents, you fixate on nucleophiles, you fixate on substrates, and then you ignore all the other issues, right? So you need to look at all of the issues, all of the considerations. Then once you have all the data, you know, if it says SN2, 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 well, it's SN2, right? But you could have one that's maybe SN1 or SN2, SN1, SN1, maybe SN2. And then from that, right, you have to make your best prediction. And in that case, right, you've got 3 things that are possibly SN1, only 2 things that are possibly SN2. Evaluate those really hard. Oh, it doesn't really tell me that it's low temperature. It's just telling me room temperature. Is that going to stop an SN1? No, that's not going to stop an SN1. It's just not like I wanted to heat it up, right? So therefore you can go, okay, well, that would also work. So I got SN1, SN2, SN1, SN2, SN1, SN1. What is that person trying to tell you? They're trying to tell you the reaction is going SN1. So when you compare these, where you'll get in trouble is by not comparing every single thing that we've gone through, right? Substrate, nucleophile, leaving group, solvent, and potential conditions if they're offered, okay? Questions about that? And again, there's lots of practice problems on the online homework for this. All right, let's move into elimination reactions. And I like the Soderbergh book, mainly because it's free and it does a decent job of covering all the topics we need to. One of the things I do disagree with it is where they put elimination reactions. We tend, historically, chemists tend to cover substitutions and eliminations together. He puts it in chapter 14. So I'll put this online, but you need to go to chapter 14.3 for the elimination reaction part. And what we're talking about here is eliminating. So in substitution, right, we had a good leaving group and reacted a nucleophile, and we substituted the leaving group for the nucleophile. So we did a direct substitution. Here, what we're doing in elimination reactions is we have something that has a leaving group. Sorry, substrate has a leaving group. We're adding a base. Okay. And we're gonna say base because if you look about like what's eliminated is the base, the proton plus the leaving group, right? So what I have eliminated from my substrate is a hydrogen and the leaving group. Like with substitutions, there's two main mechanisms for this. There's the monomolecular and there is the bimolecular. So there's the 1 and the 2. So if we look at we'll go ahead and cover a few things in one step. So here, so for E2 elimination bimolecular, what's going to happen is that base is going to come in and abstract a proton. Now, could a substitution occur? Yes, and we'll spend time on that afterwards. But one of the things to notice about E2 type bases is they're usually bulky. Okay. Why would they be bulky? Well, what would a bulky base do? It would make a poor SN2 nucleophile. So if this had been methoxide, right? So if we look at this versus this As far as basicity, is there a big difference between the two? No, if all I need to do is abstract a proton, both of these can do it about the same level, right? We got a very small variation here. But what could a methoxide do that this T-butoxide wouldn't do? The methoxide is also a very good SN2 nucleophile, but the T-butoxide is a bad SN2 nucleophile, right? Because it's big and bulky. So this proton, this base is going to pull this proton, and these electrons are going to go around and kick off the OTS, right, my leaving group. This gives me now a double bond, right? And we lose our stereochemistry because we've gone planar. And this is the only product. So what would explain the only product? Now, what do we know about SN2 reactions? SN2 reactions are stereospecific, right? I have to have backside attack. So what is going to be happening in an E2? Well, I have to, in this process, right, this proton, well, that's pretty straightforward. This just has to get close enough to that proton, right? The proton's not inside here, so this big bulky base, you know, it's got a wide range of getting in there and attacking that proton. But then when these electrons come up, where these electrons need to go? These electrons need to be going, they're just not going here, right? They're going into an orbital. And what orbital are they going into? Well, what's leaving? The leaving group. So where these electrons need to be going is into that orbital. But can they go into the front side of the orbital? Where do they have to go? They have to go in the anti-bonding orbital, right? So just like SN2, I'm breaking that bond by switching and bonding, anti-bonding lobe of an sp3, and I'm inverting it. So what I'm doing here is I'm going to put the electrons into the backside, and that's going to convert this sp3 to a p. So let me show you that, not on this molecule, but just a normal one. So if I have my hydrogen, so here's my hydrogen, and I've got my leaving group, and I've got my base. What is happening is this is abstracting that proton, right? Proton, not hydride, it's not taking its electrons. These electrons need to go into that anti-bonding orbital. What the result of that is, right, is now I've converted both of those to PP overlap, right? And I have my base and I have my leaving group. So therefore, this arrangement is called anti-para planar. For this alignment to occur, right, it has to be planar, right? They have to be lined up planar. I have to have this hydrogen and my leaving group in the same plane. If they're not in the same plane, then I don't get alignment. The other is that they have to be anti-paraplanar. If I had this arrangement, then that doesn't work, right? I'm not putting the electrons in the anti-bonding orbital. So I have to have this arrangement, right? If it's like this, that's not going to work. If it's like this, that's not going to work, right? So for an E to occur, there has to be the possibility of an anti-paraplanar arrangement. So if I look at my substrate, I actually had two possible hydrogens, right? I had this hydrogen. These are both beta hydrogens. For them to eliminate, right, they have to be one away. They have to be one away from that leaving group. So both of these are possible. But of these two, because this is a ring, right, I can't free rotate around that ring. There's only one that's going to be anti. And again, here we can think about our conformations, right? And we can think about anti-conformation. It needs to be anti to that. But over here, the best we can get is gauche, right? I can get that hydrogen, you know, next to it, right? But I can never get it opposite of. So since there's only one anti, one that's opposed to it, there's only going to be one product. Okay. So the stereochemistry of an E2 is the beta hydrogen must be able to form anti-paraplanar arrangement. So in this reaction, I only end up with one product because there's only one beta hydrogen that is anti-paraplanar, or that can form an anti-paraplanar. Questions about that? So you can already see that the SN2 is stereo controlled, right? They're stereo specific. If it's always inversion, right? E2 is going to be similar. It's a bimolecular. Therefore, the electrons have to go into the antibonding orbital, just like the SN2, right? And they're going to be stereo controlled. I have to be able to form an anti-paraplanar beta hydrogen to leaving group formation. If I can't get that anti-paraplanar reaction, then the E2 will not occur. If we look at E1, I'm going to change my substrate a little bit. Okay, so in this one, I'm not starting with a good leaving group, right? The alcohol is not a good leaving group. So the first step is going to be forming a good leaving group. And then the next step, once we form this good leaving, right, we protonated with the strong acid, the sulfuric acid. Then we get that, we get water to leave. Right, now we have that carbocation. I'll go ahead and draw in my beta hydrogens, right? That's what you're always looking for, is beta hydrogens. beta hydrogens. If the carbocation is the alpha position, one away from that is beta. Now I'm gonna divide this up and show both processes. Now, some books and some students and some answers will try and do the deprotonation here with the sulfonate. Now, the sulfonate, notice that we're using sulfuric acid, not something like HCl. The sulfonate is not nucleophilic, right? It's very stable by itself. But if we think about what's the most likely base in this reaction, it actually turns out the water is more basic than the sulfonate, right? Because the sulfonic acid has a pKa, right, of negative 7 or 8, right? And the water has a pKa of 15.7, right? And the conjugate acid of that is the hydronium, which is around 0 to -1, right? So the best base here is actually water. You want to use the sulfonate, but it's actually water. But the big part here is I'm using an acid that can protonate that alcohol, but has a non-nucleophilic anion. If I had a nucleophilic anion, what would happen? The nucleophile would attack the carbocation, right? And I would end up with substitution. So therefore, what you see in eliminations is sulfuric acid and phosphoric acid because they have a non-nucleophilic anion. So here, the water acts as my base, pulls the proton, the electrons go around to the carbocation, right? That's going to form my double bond. Similarly, in the second one, with a different proton, water picks up the proton. Again, we've got a carbocation, so it's going to be a high energy species. Now, why could it be both of these? Well, because when we go to the carbocation, right, I've got a p orbital. So therefore, the hydrogen that is going back can donate its electrons in the bottom side of that p orbital, and the hydrogen that's coming forward, right, could have donated its electrons to the top side of that orbital. So unlike the anti-bonding orbital where there's only one side that the electrons can go into, this is a p orbital, and that p orbital can accept electrons to the top side or the bottom side. So therefore, I have no stereo control with the carbocation because that beta hydrogen can be eliminated, and then the electrons can go into either side of that position. All right, questions about these? Yes. Sulfuric and phosphoric, because the sulfonate anion is not nucleophilic and the phosphate is not nucleophilic. Okay, so let's look, let's try a few practice problems. We still got a little bit of time. Let's try some practice problems on what we covered in SN1 and SN2, and then we'll work through some elimination mechanisms on elimination mechanism on Thursday before we truncate. So we'll do that. So if we look at Um, okay, predict the products on these reactions. So predict the products, and before you predict the products, predict whether it's going to be SN1 or SN2. Again, because predicting the products is going to be important to understand whether it's SN1 or SN2. Okay, and the first one, let's go ahead and look at our list of products, our list, right? So we got our substrate, we've got our nucleophile, we've got our leaving group, solvent, and then potentially conditions. Okay, so if we look at our substrate, what do we notice right off the bat with our substrate? Well, not right off the bat. We have a secondary position here, right? We notice that the alcohol is probably not a great leaving group. We'll get to that more in the leaving group, right? So we're not may have a leaving group, but the secondary is what? I noticed I have a double bond. Is that potential leaving group, the OH, next to that double bond? Yes, it's one away. If it was on it, that would be a different situation. So this is an allylic, right? Secondary, right? So an allylic secondary would suggest what? Well, this is a stabilized secondary position, right? So that's potentially an SN1, right? If we look at our nucleophile, what kind of nucleophile do we have? Well, we actually have an acid. So if we think about it, we have a chloride, but is that a good anionic nucleophile as is? Not great, right? So nucleophile, I'm going to put a question mark there for a second. Leaving group, we actually have a bad leaving group, okay? But we have an acid, so we're going to activate that. What is the solvent? Well, I have HCl. Is HCl anhydrous or aqueous? Okay. It's always aqueous, right? In fact, you can't get the water out of it. So since it's aqueous, that means my main solvent is water. That suggests an SN1. That's a protic solvent. Okay. And then I don't have any conditions, right? So it didn't tell me any other conditions. Now, when we look at the nucleophile, we have to think about first step, second step. So the first step is going to be protonation of right? So the first step is protonation of that. Now I've got a carbon negative, right? That's a pretty good nucleophile. It's also a good leaving group. But if we look at this in totality, right? What do I have? What does this suggest? I've got an allylic secondary. Is that going to be somewhat hindered? Yes, it's somewhat hindered. Can you have an SN2 on a secondary? Yes. But by making it allylic, what is the stabilization of an allylic secondary? The stabilization of allylic secondaries, you consider it to be about equivalent to a tertiary carbocation, right? So that's really good. That's going to favor SN1. The fact that I'm in a solvent is SN1. The fact that I have to activate my leaving group before I can leave, that potentially would suggest an SN1, right? So I've got everything suggesting here that I'm going to go through an SN1 mechanism, which means I need to go through the carbocation. Is this the only possible carbocation? No. Remember, we said it was allylic. That's the reason that we chose SN1 over SN2. So if it's allylic, that means that I have two possible resonance contributors. Both of these are secondary, but are both possible. Yes. Now, since they're both secondary, what does that indicate? They're going to indicate that I'm probably going to have a pretty good mixture of the two. But since it asked me to predict the products here would be the nucleophile attacking that carbocation and the nucleophile attacking the other carbocation. Let's quickly go through the next one. Here again, we're going to look at substrate, nucleophile, substrate electrophile, you can think about it that way, our leaving group, solvent, if we have one, and conditions, if there are any. Okay, if we look at our substrate here, I've got a primary position, right? That's going to be unhindered. If we look at our nucleophile, that's my nucleophile. This is a good small nucleophile. My leaving group, good leaving group. Don't have to do anything to it to get to leave. Solvent, the DMSO is dimethyl sulfoxide. It's this. It's very polar. It's one of the most polar solvents you can get, but also notice that it is aprotic. Or sorry, polar aprotic, not apolar. So it is a polar aprotic solvent. Okay, so what is that telling us? Primary is telling us SN2, good anionic nucleophile, right? That's saying SN2, the fact that it is an arrow, right? Small is SN2. Good leaving group, SN1 or SN2, right? Both of them like good leaving groups. Solvent, though, is saying SN2, right? It's polar aprotic, and then there's no conditions. So what I would think from this is, even though this is an allylic carbocation, that could potentially be SN1. Everything else here is pointing to SN2. Now, in this case, it doesn't actually determine the answer.